What's this chapter all about? Think of this word, easy and hard, and how to measure properties. Easy properties to measure: temperature, pressure, volume, mass, specific volume, mass density. You think a little bit, I could do that. How about you tell me what is the change in the internal energy, or the change in the enthalpy, or the change in the entropy? I could say UHS, but usually it's differences, right? It's like a length. Length is something pretty easy to measure, but it's a difference of position from this end to that end. So that's like a delta X. But these are hard because there's just not a entropy meter or enthalpy meter or internal energy meter. But how do they get these properties and then put them in the tables of the textbooks we use? Well, a lot of work, but basically a lot of physical measurements that go back to something similar, and then they infer the properties. So they make measurements of temperature, pressure, and volume, and then they infer what was the change in internal energy, change in enthalpy, and change in entropy. And it's these relationships between properties that allow them to make measurements on some and infer the values of others. That's the whole chapter. How do you go about making measurements on some and inferring the value of other properties? Here are some equations of state. The easiest one was P V equal to RT. Is that true? But then you had some modifications, Van der Waal, Redlich, Kwong, Beatty, Bridgman, where they make it more complex to hopefully make it more accurate over a larger range of application. But it relates the property temperature with the property pressure, with the property specific volume. See? So it's just a relationship between properties. These are examples of them. These are equations of state where it's a PVT relationship. Let's just see an example played out here. They say ammonia, they have some property data, and how does it change from a liquid to a vapor at 0 degrees C. So at 0 degrees C, they say the saturation pressure is so many kilopascal, V sub F and V sub G are given, H of Fg is given, S of F and S of G are given. Estimate the saturation pressure at -20. So what is Psat at -20 degrees C, not knowing any measurements at -20, but only the measurements at 0? So what you do is you will find that we'll derive this Clausius-Clapeyron equation. Right here it is. And you would use this relationship between properties, how they change with other properties, to infer the saturation pressure from other data. So find it at -20. Okay, well, let's take a look at this equation. We have the derivative with respect to temperature of the natural log of the saturation pressure equal to the change in enthalpy divided by RT squared. Well, let me just say what I'm going to do is this is a derivative with respect to temperature. I'll separate it, so I'll get a derivative of the natural log of P equal to change in H divided by RT squared dt. So I brought that dt over. We'll go ahead and integrate this, where we integrate from the consistent lower limit, both sides of the integral, to the same upper limit, both sides of the integral. The left-hand side is easy. We get that it's the natural log of the saturation pressure at the end. Let's say I'm going to end at -20 minus the natural log of the saturation pressure at the beginning. I start at 0 degrees C. Hopefully that made sense, how we treated the left-hand side. Now let's take a look at the right-hand side. Delta H and R come outside the integral. We just have now the integral of 1 over t squared dt. Professor, it's been a long time since I had to integrate, but this is negative 1 over t evaluated at those upper and lower limits, true? So what we're going to do is we're going to evaluate this. I'm going to do it this way. I'm going to put it like this. I'm going to get rid of that negative sign in the lower limits up here and the upper limits right there. What was our consistent lower limit? That was at 0 degrees C, and this consistent with the upper limit over here, it was negative 20 degrees C. Well, I think we're going to need to use Kelvin, so let's go ahead and use Kelvin. So 0 degrees C is 273, and negative 20 is 253 Kelvin, right? So that's what we have. So what we have is you're going to have a delta H divided by R, 1 over, basically, I'm going to put numeric values in there, minus 1 over 253. All right. So if you want to, the saturation pressure at negative 20 degrees C is equal to the saturation pressure at 0 degrees C times the exponential of delta H divided by R, 1 over, I guess I shouldn't have put those 273 here. Temperature 0, temperature negative 20, temperature 0 minus 1 over temperature negative 20. All right. So if I ran out of room here, but take it up right here. Oh, shifted it. There we go. So now if I substitute values, we'll have the Psat at negative 20 is equal to the saturation pressure at 0, 429.6 kilopascal. Exponential Fg was 1261.97 kilojoules per kilogram. The R is R bar divided by the molar mass for ammonia, and the molar mass for ammonia is 17.04 kilograms per kilomole, right? So that's 17.04 kilograms per kilomole. And then 1 over the temperature T naught is 273 minus 1 over 253, closed paren, and the saturation pressure at negative 20 comes right at 203 kilopascal. How does it compare to the table value 190 kilopascal? So it's close, but it's not spot on. It's 20 degrees different. So you extrapolated or you predicted away from the data point 0 degrees C to Psat at negative 20. Yes? Absolutely. Yeah. And so if you tried to figure out what is a better delta H, it'd be a lot better. You know, temperature dependent properties. But it's just to show an example of property relations and how to extrapolate. So the title of the chapter may not seem all that impressive, but they're relationships like mathematical relationships. This is the chain rule. Do you recognize that? So if you had a function z and it was dependent on x and y, then you could say, how is a small change in the output related to small changes on the inputs, x and y? And this is the relationship there. True? So this is with holding x constant, isn't it? Hold it. Yeah, this is holding x constant. I got a typo right there, right? Do you see that? Yeah, chain rule. What about this rule right here? This is a mathematical relationship, and it would hold on a function just like this. And this one's called the reciprocity rule. Reciprocity. How many people heard that word before? Reciprocity. No? Yeah. It's like if I push you, you push me, you know, kind of like you learned it in kindergarten. You pick on me, I pick on you, whatever. You take my toy, I take your toy. Now it's like it goes from kindergarten up to nations. You bomb my city, I bomb your city. You know, I send your troops over, whatever. Our troops are gonna, whatever. But it's tit for tat, tit for tat. So anyway, this is a relationship. There's another relationship. It's a cyclic relationship. So this is also true and can be shown. So if you take the derivatives, multiply it by another derivative, multiply it by another derivative, you get -1. No, that's not a typo. It is negative. It looks like the z's would cancel, the x's would cancel, the y's would cancel, and you get 1, but it doesn't. It's a -1 on the relationship. So it's a little review of mathematics. Here, let's try work out this problem. Check the applicability of the reciprocity relation using the ideal gas equation. Well, the ideal gas equation, PV is equal to RT, right? Just have to pick one. Do you want Z to be X, P to be X, Y, or Z? If you let it be Z, fine. Then this one can't be Z, it needs to be like X. And that one needs to be Y. You see what you're doing? You're kind of taking the general form for this particular relationship, translating it. So if I wanted to, I would say that if I wanted to check this out, every time I see an X, substitute Z, not Z, sorry, substitute V. And every time I see a Y, substitute a T. So that's a T, and that's a V. And what are we holding constant? P. So to check the applicability of the reciprocity relation, I'd like to say is take the derivative of V with respect to T holding pressure constant, multiply it by the derivative of T with respect to V holding pressure constant, and see what you get. What do you get? Do you get +1 or not? So what you have to do is you have to compute this derivative. So take the equation, say V is equal to RT over P. True? Now do this. What is the partial of V with respect to T holding pressure constant? R over P. Do you agree? So it's equal to R over P. Now, how about this one? Temperature. So temperature is equal to PV over R. True. What is the partial of T with respect to V holding pressure constant? P over R. Multiply that by P over R. So this was the first one. This is the second one. And they cancel. And it's equal to 1 as you set out to demonstrate. Yes?
Does P always have to be Z?
No.
Why do we know that P is Z?
Don't have to. You could change it up. You know what? Over the spring break, if you're really bored, come in here and just change it and make it work. So here's another one. Use the ideal gas equation and check the cyclic relation. So we'll start with PV is equal to RT. You tell me which one you want to be the X.
Let's go with B.
x. Which one do you want to be the y?
P.
P. And which one do you want to be the z? Your default already. So now I go ahead and translate this. The partial with respect to pressure, with respect to temperature, holding V constant. Did I do the first part right? Multiply that by then the partial temperature with respect to specific volume, holding pressure constant, multiplied by the partial with respect to specific volume, no, partial of V with respect to pressure, holding temperature constant, and now I want to find out if that truly is equal to -1. So on the side, I take the time to do these derivatives. So P is equal to RT over V. So the partial of P with respect to T holding V constant is, what is that equal to? R over V. True? So this is R over V. Now the next one, I want to get T is equal to PV over R. What's the partial of T with respect to V holding P constant? P over R. True? And then we have the last one. We have V is equal to RT over P. And we want the partial of V with respect to pressure holding temperature constant. Negative RT over P squared. True or false? Do you like that one? Negative RT over P squared. Do you like it? Thumbs up if you do. Good. So we get negative RT over P squared. And now we just see what cancels. One of the P's goes. One of the R's goes. But PV is equal to RT, so they go. You're left with -1, just as we set out to do. There's already some property relations we've been exposed to out of Chapter 6 when entropy was a new property. And actually when we had the new property entropy, we tried to put it in terms of changes in internal, changes in volume, changes in enthalpy, changes in pressure. So these are examples of property, thermodynamic property relationships, and they're a fundamental building block of a lot. This is one way we can start with those and get new relationships. So start with the first of the two TDS equations. Here it is. And now think about, just pick that U, internal energy, is a function of entropy and specific volume. If that's true, then a small change in internal energy can be related to what? The rate of change of internal energy with respect to, trying to just adapt this here equation, which is in general applied to this, but now we're applying it to there. U is a function of S and V. So here, U, S, V. So every place I see Z, replace it with U. Every place I see X, replace it with S. Every place I see Y, replace it with V. So we pick up the partial with respect to S, holding V constant, times ds plus the partial of U with respect to Y is V, holding X constant, times dV. True? So just by mathematics, if U can be thought of as a function of S and V, then a small change in U can be related to a small change in S and a small change in V. You just compare, rewrite this equation to have du is equal to T ds minus PdV. Now I compare and I say, hey, is that exactly the same? Sure. Is ds exactly the same? Sure. Is dv the same? Yes, that's the same. And so what has to be equal is that this has to be true. T has to be equal to du ds holding v constant. Likewise, negative p is equal to du dv holding s constant. So here is how they develop a lot of relationships between properties, just like this. Okay, so here's two new ones. You do the same thing with the second TDS. You get two more. And then you introduce new functions. Gibbs, you probably heard of before if you took a chemistry class. Gibbs function or Gibbs free energy. It's the same terminology, but the recommended term used in this textbook as well as a lot of others in the literature is the Gibbs function. It's defined as a property G equal to H minus Ts, and also the Helmholtz function is equal to internal minus Ts, okay? So you can learn more about what the physical interpretation or utility of these functions are, but they are important, especially in chemistry, for the Gibbs function. So you get more functions and more derivatives and more relationships, and you get a whole sequence of them. And you'll even get what Maxwell put together many years ago, fundamental relationships. Here's 4 of them. These 4 between properties, thermodynamic properties. They look pretty cold and hard and a little abstract, don't they? It's just hard mathematics. But this is the fundamental building block by which some properties can be measured and others inferred from the measurements. Let's do this. Let's talk about how to evaluate. Remember, the hard was how to get changes in entropy, in internal energy, and enthalpy. And it's easiest to start with only considering phase change. So if you consider phase change, remember you have a pressure temperature diagram, PT diagram. Go back, one of the most important thermodynamic chapters, or chapters in thermodynamics, is properties chapter, chapter 3 in our textbook. Go back to that chapter, really study it. But you'll have a point and a line and a line and a line like this, right? That actually goes up, up, up. This goes down, down, down. This ends right here. This is the CP. This is the TP. This region out in here was all where it's gas or vapor. This region over here is all where it's liquid. And this region over here is all where it's solid. Typical PT diagram. So what was CP, critical? What was the TP, triple point, true? Okay, so what happens along this sequence of lines right in here? Phase change going from liquid to vapor, boiling or condensation. What about from this point all along this sequence of lines or states? Solid to gas, sublimation. Anybody ever see dry ice and it just vaporizes from solid right into vapor? Also, ice cubes in a tray in the freezer, after many months, if you pop them out, you'll say, hey, this ice cube was full, now it's sort of eroded. If you've ever seen that in a freezer. Sublimation. This one is just freezing or melting. It's that phase change. Well, if you start with, let's say, this TDS equation right here, and we're going to say to ourselves, during that phase change, I am not going to change temperature. Temperatures is, you're just, think about this, probably the easiest one, going from F to G, true? Just going from F to G. You're sitting there at the same pressure, the same temperature. So the pressure's not changing. And so what you get is you get the temperature times the change in entropy is equal to the change in enthalpy. That almost seems too silly. Push it from the limit such that it starts at saturated liquid, saturated liquid, and it goes to saturated vapor. Beyond that, it would not be just a single, it wouldn't just be a change of phase. It would have more than, it would go from like subcooled liquid to superheated vapor. But from saturated liquid to saturated vapor. This equation then is saturation temperature times S of G minus S of F is equal to H of G minus H of F. How could you use this type of information? If you could somehow get a measurement on H, enthalpy changes, you could infer the change in entropy. You could infer the change in entropy. That's how you would use it. You would say, oh, SFG is equal to HFG divided by Tsat. Now, if you take your property, any table, open it up, refrigerant, ammonia, water, and you say to yourself, will this work for every one of them at all these different pressures and temperatures? It better. It better. Make sure that this temperature is in, remember, Kelvin, absolute temperature scale. Here's an equation. It's called the Clapeyron equation. This equation right here. Okay? And we want to challenge ourselves. We want to go ahead and derive the Clapeyron equation. Okay? So how do we derive this Clapeyron equation? And this is applicable. It gives us, let me try and interpret it first. What is dp dt, sat? So go back to our pressure temperature diagram, like that. And so think about, I could make of changing different pressures. I could get sequence of different temperatures and map out this curve, those sequence of states, true? I could then differentiate, that's what this is doing, and get the slope at any point along that curve. And then I know that it's equal to the change in enthalpy divided by temperature, change in specific volume. Let me kind of group these and say hard to measure, hard to measure, hard to measure, hard to measure. Which of these four groups, group 1, 2, 3, or 4, if I did the Roman numeral right, is the really hardest one to measure? I could, and let's maybe not do the hardest one. What's the easiest one? Isn't 2 the easiest conceptually? It's like temperature. I think I could have some confidence in getting some temperature measurements, right? Volume changes, going from saturated liquid to saturated vapor. Have that sealed piston, measure the cross-sectional area, know the mass that I put in there, have it saturated liquid, see the piston's height right when it starts to change into vapor. That'll be V sub F. That'll give me V sub F. Then the volume, when it stops, there's no longer any liquid in there. Now it's saturated vapor. So I think this one is doable as well. 3. This one we just talked about. You just get a bunch of P and T and then get the slope. This one is the hard one, HFG. So this tells us how to get HFG. We could get HFG if this equation was true. We wouldn't get it from heat flux measurements. We would get it from temperature, volume, and pressure measurements. That's it. Temperature, pressure, and volume measurements, and then you get HFG if this equation is true. So how do we get this equation? Let's derive the Clapeyron equation. Well, going to consider constant pressure phase change. So we have dH is equal to T ds. We've recovered that already. Actually, let me back up. Let's start with one of the Maxwell relations. one of these Maxwell relations. What we want to do is we want to look for this one right here. Okay, this may not look like the key starting spot for this derivation, but it's very useful. So we bring across one of the Maxwell relationships that the partial of S with respect to V holding temperature constants, the partial of P with respect to T holding volume constant. Well, if it's during that in the two-phase region where you're changing phase, then the pressure is a function of temperature only. True? So this whole partial derivative just goes to P. It just goes to the ordinary derivative where the saturation pressure is a function of temperature only. Okay? So that's how you handle reducing the complexity of that right-hand side. It's not a partial derivative where you have function of two independent variables. It's a single function. All right. So then we have to change a phase, you have the S of G minus S of F divided by V. V is V sub G minus V sub F. Okay? So the change in the saturation pressure as a function of temperature is equal to this SFG, if you want to call it that. How much is the change in the entropy divided by V sub FG, or just leave it as S of G minus S of F and V sub G minus V sub F. Well, we already saw from this relationship that ds is equal to dH over T. So we can replace by H of G minus H of F divided by T. Replace that term for the change in S. You have V sub G minus V sub F. And that's it. I hate to say it, but there you go. See this? This is what we wanted to come out to. Isn't that what we have? Sometimes the results are anticlimactic. Yeah, but you have to know where to start and how to get there. Right? Right? Okay. Well, how about this Clausius-Clapeyron equation? Isn't this the equation that we used already as an example? Well, how do we go from the Clapeyron equation, which we just derived, which I'll rewrite right now? We start with, we have the P dt saturation pressure with respect to temperature is equal to, we had the HFG, here this is HFG or delta H, HFG, divided by T times V sub G minus V sub F. Okay. If you look at it, there's one equation, right, one approximation right away, that V sub G is so much bigger than V sub F typically. If I look at the volume occupied by a liquid versus the volume occupied at the same pressure by the vapor volume is so much larger, you neglect it. So that's the first approximation. The second one is, which is, you have to check into the second one. But at low pressures and relatively high temperatures, not close to the critical point, you can often, it's often a good approximation that V sub G is equal to RT over P. What? What's RT over P? Do you recognize that second equation? The vapor behaves as an ideal gas. Not near the critical point, okay? But down far away. In our textbook in chapter 3, there's an excellent plot for steam showing you in percentiles when this steam near the dome, but it's not near the critical point, but down at the saturated vapor region, behaves as an ideal gas. It's shown to be justified in chapter 3. So there you go. Well, when you make these two approximations or assumptions, this equation becomes the derivative of P with respect to temperature, saturation, is equal to HFG divided by RT squared. Whoops, with the P. True? With the P. I need that P. True? We're almost there. You just bring the P over, so you have 1 over P, derivative of P with respect to T for saturation. Well, what's the mathematical relationship that I need to recall and use it? If I said, what is the derivative of the natural log of x with respect to x? How many people remember that? The derivative? It's 1 over x, true? Is that what you were thinking? Okay, here's another one. What's the derivative of the natural function of y, which is a function of x, with respect to x? What is that derivative? Derivative of the natural log of y, which is a function of x, but I want to differentiate that with respect to x. Is that 1 over y times the derivative of y with respect to x? Look good? So what happens is you just recall, you say, oh, look at that. That's the derivative of the natural log of saturation pressure with respect to temperature. And then you just continue to leave the right-hand side alone. Okay, and there you go, QED. That's what we wanted to show. Now you can write this. I tried to put it for going from liquid to vapor, HFG, but you don't have to do it. It works on any of those phase change regions from F to G, from I to G, and from I to F. Works on any of those three. Now, the Clausius-Clapeyron equation, the Clausius is the two additional assumptions. This only works I to G and F to G south of CP. How's that? Away from CP. You don't want to push it up near the critical point. But there you go. Well, with that, I'm going to go ahead and stop.